So in the third part of the tutorials on electrolysis, we're going to start off with electrolytes and non-electrolytes. So firstly, in electrolytes, you know most of the stuff about it. It's always in the fused or molten state, or it's in the aqueous state. So, and you know some of the examples as well. But among these electrolytes, there are further subdivisions. Electrolytes, this is just the main heading. Now under this you have strong electrolytes, strong, you have weak. Now obviously there is a sort of system. How do you decide which one is a strong electrolyte, which one is a weak electrolyte? And there has to be some sort of a mathematical formula to do it. So it's not really a mathematical formula, but it's a rule that is followed. There's a term called degree of dissociation. It's too long to write. I'm just going to write D of D. Now what this means is that we've done dissociation before, so it's basically an ionic compound breaking into its ions. So degree of dissociation, it's a number that tells you that out of 100 molecules, how many of the molecules of that compound, that is of the electrolyte, break up into ions. None of the times, practically, it will never be 100%. But let's take a realistic example, say 45%. If it's 45%, this means that if you have 100 molecules of any this compound whose degree of dissociation is 45%, that means that 45 of those out of the 100 will break into ions. The rest will not. So now the way you determine whether an electrolyte is a strong electrolyte or it's a weak electrolyte. Now if the degree of dissociation, it's represented by alpha. Now if the degree of dissociation is more than 30%, then it is a strong electrolyte, and of course if it's less than 30, it's a weak electrolyte. Now some of the characteristics, um, now these ones, strong electrolytes, will break up into only ions. They will leave behind little molecules, while weak electrolytes, you can see they'll definitely have more number of molecules, lesser ions. So they'll have a fair amount of ions as well as undissociated molecules. And also these ones, since they break up, weak electrolytes, since they break up into little number of ions, which in turn conduct electricity, weak electrolytes as a result will be poor conductors of electricity. I'm going to write that down. That's an important point. Poor conductors. On the other hand, strong electrolytes will be good conductors, so you can pass a lot of current through them. Now, other than electrolytes, there's also non-electrolytes. You could guess from the word that non-electrolytes are those which have a degree of dissociation, that means alpha, is equal to 0%. And I don't think I said that before, but percent is because we're talking about out of 100 molecules, how many will break up into ions. So that's why I use the percent here. So there are some compounds that in the fused or aqueous state don't break up into ions at all. These are called non-electrolytes. So these contain molecules only. I'm going to write that down because that comes pretty often. M only. Weak will contain M plus I, while strong will contain I only. So from this you can also tell that non-electrolytes will not conduct electricity at all. um, Keep in mind that weak electrolytes are poor conductors. That doesn't mean that they won't conduct electricity, but they're just less efficient at doing it. So these ones do not conduct. Okay, now just going to go through some very quick examples here. For strong electrolytes, you could write, say, you could divide it into acids. Now, most of the strong acids are strong electrolytes, so you could write HCl, you could write H2SO4. I think there's a full list. It should be given in your book, or you can go online and search as well. And you should do this because there's a common question in section A. HCl, H2SO4 are strong. For bases, again, the strong bases are also strong electrolytes. So NaOH is strong, KOH is also strong. Now for salts, there's sodium acetate. I think the better example for you right now would be potassium chloride. Potassium chloride. So that's all there is for strong. Now coming to weak. Now for weak electrolytes, again we can write weak acids, weak bases, and salts. So under weak acids we have acetic acid. So that is CH3COH. You'll do it under hydrocarbons. And there is carbonic acid, but I think there are more acids, carboxylic acids, that are you'll do them under hydrocarbons. So those are all relatively weak acids, and those come under weak electrolytes as well. Now weak bases, you have NH4OH, you have MgOH. I'll just write one of them here. NH4OH, I think you could learn. And under salts, ammonium acetate, lead acetate. So you could learn it from your book, and you really should. So, and also, yes, non-electrolytes, some of the common ones: distilled water. And distilled because absolutely clean water containing no impurities, only that will have nothing to conduct uh, the electricity. This water on its own will conduct electricity. It has some impurities. You also have stuff like benzene, which is C6H6. You have alcohol as well. So again, I think you'll understand more of that when you do the hydrocarbons chapter. But for now, just learn whatever's given in your book. I think two or three examples should be sufficient. Um, so I think that's it for uh, this section. Also, a few ways to remember this. Um, Covalent compounds, most of them are non-electrolytes. Just remember that as a fact. And when you have strong acids and bases, like over here you have NaOH, you have HCl, or you have salts that are derived from strong acids or bases. So, for example, KCl over here, you have the K from a strong base, you have the Cl from the strong acid, so you have a strong salt over here. All of these are usually very strong electrolytes. And similarly, weak acids, weak bases, and salts that are derived from weak acids and bases are usually come over here in this section. So that's a way to remember it. Now, I think, yes, now coming to, it's one of the most important parts. Now, the next concept is something called preferential discharge. Now, in there's some cases when your electrolyte will have not one but two cations or two anions. I'm just gonna give you one example right now. Okay, so say you have an aqueous solution of NaCl. Now aqueous means that you have NaCl and you have it in water. So these are your two compounds. Now this is going to break up into Na plus and Cl minus, while this H2 over here will break up into H plus. Oops. Sorry, H plus as well as OH minus. Right, so you see now that in the electrolyte there'll be two cations swimming around and they'll be racing to see which one goes to the cathode. So there's Na plus and there's H plus. Similarly for the anode there are two competitors, that's Cl minus and OH minus. Now it's not possible that both of them are discharged. Both of them being like both of the cations are discharged and both of the anions are discharged. So only one can be discharged at each electrode. So this gives rise to the concept of preferential discharge. Preferential discharge. Okay, so like you have your reactivity series, you also have something called electrochemical series. Now these are the two series actually. First one is for cations. Now it's actually I can't write it all down because it's pretty long, but it's just a series. It's a series of elements. I'll tell you a good way to remember it. It's pretty easy. Uh, I'll just come to that. But as you go down, the reduction potential increases. Now reduction potential increases. This is nothing but the tendency to get reduced, and reduction is gain of electrons. So it is basically how much does the atom want to how much does the ion, rather, in this you have ions not atoms, how much does the ion want to gain an electron. So the one that wants to gain an electron more than the other will be placed below over here. The one that doesn't want to gain at all will, not at all but relatively to this one, this will have a much lesser reduction potential. So for cations, that is metals, metallic ions, this is the same. It's the exact same as a reactivity series, that is K, Na, Ca, Mg, so on. But just the only change actually comes here, where all you have to do is switch Na and Ca. That's it. The rest is all the same up till silver. So that's all you need to know. Just switch the Na and the Ca. So the Ca comes second, the Na comes third, and you're done. That's your electrochemical series for cations. Now coming to anions. Now this will be new for you. So I'm gonna write this down. It's shorter. OH minus, which is hydroxyl ion. There's I minus, which is iodide. Br minus, which is bromide. Chloride is Cl minus. NO3 is nitrate. NO3 minus. Sulfate is SO4 minus. SO3 is sulfite. Remember that. And the same thing here. Reduction potential increases. So this is for anions. Now a way to remember this, I just made a very senseless sentence. It's, oh, I brought chlorine, no, so I know it doesn't make sense, but at least it helped me remember. It doesn't have to make sense. You are, of course, you can make up your own abbreviations like that, because what works for me will not work for you. So, but that's how I remembered it. Reduction potential increases. Now, how do you check that which one, say you pick any two cations, in this case we have Na and H plus. H plus would be somewhere near the bottom. So if I'm given these two, how do I decide which one will get discharged? Now, for metals need to gain an electron, right? So they need the one that will have a higher reduction potential will want more, will not want more, but it will have a higher tendency to gain that one electron. It'll fight harder. And reduction potential increases as you go down. So obviously the one that is at the bottom, which is H, will want an electron more than Na. So whenever you're looking at cations competing for getting discharge at the cathode, the one lower, this is in cations, remember that, the one that is lower will get discharge first. They'll get the preferential discharge. Now it's the opposite over here. Same thing, reduction potential for say SO4 and OH. SO4 will be much more, OH will be much less. But what you need to remember here is that anions actually need to lose an electron. So lesser the reduction potential, more will be their tendency to lose that electron. So say you have OH minus, and let's take this example here, and you have Cl minus. So it's clear that Cl minus will want to gain an electron much more than OH minus, but the converse is also true, that OH minus will want to lose an electron much more than Cl minus. And when you talk about anions, we're talking about losing that one electron that is here. So in anions, it'll be the opposite. The one that is higher will be discharged first. Now you can just learn these. So when you talk about anions, the one that is higher in the series uh, will be discharged first. Now I suggest that you just learn it like this for the exam, but in case you forget it, you can just go through, just think of the logic that I told you, that cations need to gain an electron and reduction potential increases as you go down. Just draw the chart and you'll get it. And I'm out of time now, so I'm going to continue with a few examples in the next video.